So a classic example of motion that's undergoing constant acceleration is an object in free fall. Okay, so free fall is an example of motion with constant acceleration. Okay, so what is free fall? Free fall is when an object moves or is only under the influence of gravity, no other force. Okay, so for to have perfect free fall, we would need a vacuum. What a vacuum is a chamber that has no air resistance. And if you had this, if you took a feather and a hammer and with no air inside and you drop them, they would land at the same time. Of course, this doesn't happen in reality because there's air resistance, and air resistance affects motion. So if you have air resistance, you technically don't have free fall because there's air resistance. It's under the influence of gravity and air resistance. So, having this condition for free fall is basically impossible on Earth. But there's a lot of times where we can make the free fall approximation. Okay, so with no air resistance, Galileo's discovery was that all objects accelerate at the same rate. Okay, no matter what their mass is. Okay, which is kind of a little bit counterintuitive, but the idea is that if there's no air resistance, this feather and hammer would fall at the same rate. Okay, and we can see this from, if you look at some videos from the moon where they drop objects. Okay, you'll see that actually does happen. But on Earth, there's lots of scenarios where we can still use this approximation, and some of them are shown here. So like if you drop a rock from, maybe like a 5th floor, or throw a baseball, okay, we'll say that free fall approximation is valid in these cases. Okay, you just have, there's no rule. It's just how good the approximation is. We can use the free fall approximation for a skydiver, but it won't give you very good results. Okay, so because there's lots of air resistance in this, a skydiver, you have a parachute, of course there's lots of air resistance. Okay, so in this case, free fall approximation is not valid, so we wouldn't be able to use constant acceleration equations for this type of problem. Well, so how, if we dropped a baseball or a hammer, we could measure that the acceleration on Earth is 9.8, roughly 10 meters per second per second. Okay, we give this value a special letter, which we call small g. Okay, so g is always positive. Always positive. We will give it a direction by giving a negative or positive in problems, but the actual value of g is always positive, and it varies on different, and it changes due to different factors, which we'll discuss later. But on the moon, it's a lot less. It's 1.6. This is why astronauts, they can bounce around the way they do. And on Jupiter, we feel really heavy because they have acceleration due to gravity is 24.5 meters per second squared. So that's 2.5 times what we have here on Earth. Okay, so let's look at how this works in a scenario where you drop a ball. Okay, so if you drop a ball, you have acceleration going this way. Okay, you have negative acceleration because your velocity is increasing in a negative direction. Okay, now if you throw the ball up, okay, let's say it's under the influence of gravity alone, the acceleration on the way up is still negative, even though the ball is going up. Because it's slowing down in the positive direction, we have negative or downward acceleration. At the very top, it comes to is the turnaround point. Okay, where the ball comes to an instantaneous stop. And then on the way down, again, we have acceleration that's negative because it's increasing speed in the negative direction. So if we were to draw a velocity time graph, okay, we would see that the velocities would be constant. they would be, the slope would be constant because at all times the acceleration is constant. So we would, if we toss the ball up, we would have an initial positive velocity, and that velocity would be decreasing. At the very top, right here, it would be zero velocity, and then it would be moving down with increasing negative velocity. Okay, so the slope is constant, and if we calculate it, it would equal negative 9.8 meters per second, or this would be equal to negative g. Okay, now one thing that's important is, free fall doesn't necessarily mean that the ball is falling. You could be going up, just like it is over here. The ball is moving up, and it's still in free fall. So it's moving up and slowing down. Okay, so we still have free fall acceleration because the ball is under the influence of gravity alone. So some notes: free fall is constant acceleration, so that means, so therefore all our kinematic equations hold. Okay, so we can, and what we use is, instead of a, for ay we use negative g, which is negative 9.8 meters per second squared. This is for problems on Earth, of course. If you have problems on the moon, you would use the g for the moon. So just a couple things. This g value is not called gravity. Don't call it gravity. It's called free fall acceleration. So free fall acceleration. And again, a little note here, we use negative 9.8 only for problems near the surface of Earth. So let's do a quick example. So we have a balloon that's fired from the ground straight up at a velocity of 30 meters per second. What was the maximum height reached by the balloon? So we have a ground here, there's a balloon shot straight up, so if we do a motion diagram, the velocity would be decreasing on the way up, come to a stop at 0. The V initial was 30 meters per second. V final, because it comes to a stop, is 0. Because it's under the influence of gravity alone, we're going to ignore air resistance. Our acceleration would be negative 9.8 meters per second squared, and we want to find delta y, the height. Okay, so we have equation 1 as Vf is equal to Vi plus a delta t. Since we don't have time, that equation won't work. So the equation that we need is the second equation, delta y is equal to Vit plus 1/2 a t squared. Shoot, we don't have time, so we can't use that equation. So we'll use the third one, which is Vf squared is equal to Vi squared plus 2a delta y. So V final is 0 squared, that's easy. V initial is 30 squared plus 2a, which is negative 9.8 times delta y. And if you plug that into your calculator, negative 30 squared divided by 2 times negative 9.8, you will get a delta y of negative 30 squared divided by 2 divided by 9.8. You should get about 45.8